Well, Zoltán, you can talk a little bit about yourself.
While I set up my laptop?
Yes.
So I work from DLR, but at DLR, but I was doing my PhD here, actually there.
Okay, guys, so we're not going to flip the camera, sorry.
with Nico and Radu and some other guys. I think us three were contributing maybe at the beginning at what then after many iterations became PCL. And I've kept using it. It's just that at DLR we are not really making things public as of now. Even though DLR has lots of in-house developments also for 3D processing, for alternatives to ROS and so on, there are still some parts which are better tackled in these open source projects. So there are applications where we do use them, and I'm going to be talking about them. And also, lately we've been also doing some development to the core PCL module, and I'm going to present that. They will be pushed, or a pull request will be sent hopefully soonish for them. Right. So as I said, there are many users, and these are especially in the mobile robotics group. So with things like rovers, quadcopters, and mainly using stereo cameras. And of course, PCL and the so-called open source cloud is useful if you develop something on your own, and then if you want to publish it, reviewers usually ask for comparisons. And since you don't want to re-implement every algorithm on yourself, then you take open source libraries where these are implemented and compare your results on those. It's a bit difficult to use. This was meant mostly for the developer session. These slides where I was about to complain about the Linux distribution and custom
management. Do it now. We're okay. We're here.
This is now live, so no, everything is great. Now we got the new Linux distribution, so it's getting better. I remember we had still fights here, even at TOM. We were supposed to use some old Debian, but we just didn't. There's a bit more difficult because we don't have good rights. Okay, and the new developments that I'm going to be talking about is new shape models that are going to come to PCL, and also mention some other things which are published, and anyone is free to re-implement that, but it's difficult for us to give that out. There has been also some mentoring that I did for Google Summer of Code, where I still have a bunch of code to be reviewed, and yes, let's talk about that.
3 months.
So the new shape models. First, the Manhattan frames, which is just if you imagine Manhattan very rectangular, that's the same also in indoor environments. Most man-made structures have like some internal some intrinsic orientation, like 90 degrees offset normal directions. And even if the scene is very cluttered, so you don't see like 3 walls or 6 walls of the room, you can still guess what it is based on just patches here, patches there. So there is a maximal subset of normals aligning to a coordinate frame, and this is what in literature is called the Manhattan frame. And finding this maximum number is a perfect use case for RANSAC. So we implemented it using RANSAC, and it will be pushed to the central consensus module. Then building up on this, you can then also fit the sides. So try to estimate the cuboid sizes and extents. two methods from literature. First, torus, which I think was missing. Did I get it right? Yes. And the surfaces of evolution, which was done by Nico here and published in 2009, and it somehow never made it into the main branch of PCL. But now Stefan re-implemented it, so it will be hopefully released. And another one is a polynomial surface model, so that is for smooth surfaces. Yes, coming back. Manhattan frames are difficult to visualize because they don't exist. You know, I mean, they are like virtual entities or an alignment. But if you visualize the coordinate frames, maybe this is the best picture, or these are the best picture with the frame axis, where red is x, blue is no.
Y.
Y and green is Z. Is it blue Z?
Sorry, red, X,
yes.
RGB. So
yes,
the
it's another way around. But the important thing is you can see some distribution. So most of the red is here, most of the green, the blue is here, the green is kind of overlapping with the two. Or here every axis has its own like space where it can rotate to. These are just different ways how to represent them uniquely, so that each 24 possible rotations that describe the equivalent Manhattan frame are unique. So that was one problem in the implementation, to get them all into a unique representation. And then by just the standard random sampling and checking which one has the most inliers, you can get them pretty accurately. So we compared to a very complicated method that was estimating actually multiple Manhattan frames in the scene at once. We would have to with Transect. The problem is that you always have to do this sequentially. But if this is the ground truth, these are the distribution of the angular differences to the ground truth. You can see that most of them are not too much of, so an average, let's say like, I don't know, 10 degrees with some outliers which are like completely wrong, and then the median is like 15 degrees off. So for a Ransack method, which is much faster than whatever was published, this is quite okay. So if you just want the rough orientation of the scene where you are in. So the extensions for cuboid fitting, you can see it here for one cube. If you do it like in the traditional Ransack style, where you sample endpoints and you want to estimate the model out of these endpoints, that's a bit difficult for cubes, because you would need to by chance sample corners, and if you don't sample them, then you grow your cube only until there are samples, which is not very good, and also not very robust if there are like multiple cubes. So what we did is you start a region growing step after we sample to find the sides, and then results get nicer, but it's not the traditional Ransack, because model parameters are estimated also using inliers, which could be hacked into the current PCL framework. It's not traditional Ransack. So some evaluation. I don't know if it's if you care this much detail about this much detail. What I want to focus on here is that just maximizing the number of inliers doesn't always give you the best results. So what we found is that the rating of models also based on how often do they violate I don't know what's the right word, free space constraints. So if there are model parts between measured points and your camera, so they are actually what was measured as free space, that should be penalized. If they are in occluded space, then you don't care. If they are in occupied space, then it's good. But this penalization should be included. This was also published there in the paper with Nico, because for more complicated models this actually helps a lot. So you can see that without this occlusion rating and with occlusion rating, without this for the extents of the boxes. So you don't get weirdly extended boxes into free space like this. So two other models are the torus and the surface of revolution. The surface of torus, you know, the donut. Surfaces of revolution are an axis of rotation and the curve that is rotated around. We just have a polynomial curve. In theory, we could rotate anything. Maybe that would be a good extension to have also different surfaces of revolution. But now we have like just a polynomial line that is rotated around the axis. Again, estimated in a ransack-ish way to sample a subset of points, estimate the axis, get the curve, check how many inliers it has, and iterate until you maximize the number of inliers. The last shape that I would talk about are the smooth surfaces. I don't know if this is not very visible, but here you can see like the carbon fiber structure between two robots, and what they do. I mean, these are all bit individual, so no two plates are exactly the same. So when you want to use this for production, like airplane wings and things like this, then you need to know its physical properties. And what people have been doing is putting a bunch of markers on it, or maybe these types of markers, different types of marker, making a specific movement, like you're doing an impulse and checking its movement and getting the, I'm not no physicist, so some physical properties out of it. And so you can see this is in the middle of the movement. And the problem with these markers is that they don't really stick very well to this carbon fiber, or if you stick it, then it's hard to think of. They get occluded and it's very sparse. So we have depth sensors, right? So we can measure this, but you would need to detect this shape in the scene, and also find track individual points. So you find corresponding points between like in a video to know to be able to do this analysis. And what we did is using ransack to finding the largest smooth surface in there. It's not really perfect, because if you can see here, there are like in a very dynamic movement, there are like bends in there which are not like a simple depth function. Here there is like two depth values which correspond if that would be possible to that point. So you see that here parts are then also not perfectly matched. But when there are like smoother movements, then you can most of the time estimate them quite okay. And what we do here is we sample again a set of points and fit a polynomial to it, and try to increase the number of inliers and reduce the number of polynomial terms, like coefficients, like high order coefficients, by an expectation maximization style algorithm, where you try to smooth it out, so to say, and make it simpler at the same time. So it's still not perfect. You see some. I mean, it's ransack. So even if you set the probability of success to 99.999%, you still get some cases where it doesn't work. Like here, or it sometimes gets also part of the frame that holds the structure in it. But those are, and in the data at least, those are the smooth surfaces, the largest smooth surfaces, and you need some cross-processing them to get to the real surface. Right, and the next topic is how to combine all these methods. So let's say you have a big scene and you want to look for some object that lies on the table, and what you would typically do is, let's say, find the table first. To find the table first is more efficient to know what is the up axis, so you would need to find the up axis first. Then on the table you define the region of interest as above the table by a convex hull, let's say, of the table inliers, and then you look for your specific I don't know, cylindrical object like the speakers where between a min and max height above the table. And all of this was there's a lot of pipelining, and if things get complicated, this gets more difficult to pipeline. And if you do this with C++ code, it's long. If you do it with XML launch files for ROS, don't even start. And so we found that actually we could describe this as in words, as I just did. That is, let's say I have a plane which I will now call table. I define a volume which is for the tabletop, which is outside of the table. Outside here means in the positive normal direction. There is a sphere in the tabletop. You should do some pre-clustering because they are like individual clusters, which would speed up the search for NSEC. Its radius is between 5 and 10 centimeters. Then I define a new volume which is inside this lampshade, and there inside the lampshade I am searching for two cylinders with some radiuses. And you could make a whole tree of so here are two searches. And yes, this was published in the special issue edited by Mateos. You can look it up there. Also how this was done. And then you see that if you do this like in this hierarchical method, you find the plane, the lampshade, and the two cylinders inside. And I mean, I don't have to tell, but if you just throw every data in and search for them, then you find something. But it's definitely, this one has definitely more inliers than that, but it doesn't have the right constraints between them. So how did we use this? It was in a competition. Well, it started out as a competition, then it was just a camp basically where everybody was showing what they did with our robot here, which is for the lightweight rover unit, which starts from a base object, has to explore some unknown area, find two objects. One of them is relatively in plain view. The other one is occluded somewhere. Bring it back to the base object and put the cup on top. I think I have a new slide. Yes, I will have a new slide where this is in plain. Put the one on top. Put the other inside. Switch the flip and flip the switch and do this in. Completely autonomously with I mean, it's simulating a moon-landed robot, so you have very low bandwidth and lossy communication with only very narrow windows where you can send commands to the robot. It has to be done in an hour, and because the communication was just so difficult, we just ended up doing it completely autonomously, so not influencing at all. I just want to show how this went. Is it starting? Okay. It's always the thing with videos, right? Maybe I have to create it here. So you start off with exploring the terrain. Here the mapping is actually internally also using PCL. It's using a graph SLAM approach after the visual geometry, where local maps have to be matched, and that is done with based on correspondences on with shot features and then ICPing them. At least that was when I was involved in it. If they didn't change it in the meantime, but I think that's the one being used. So you are creating these local maps, matching them together. The navigation is purely done based on stereo vision and fused with an IMU, and that periodically it was looking around and searching for objects. Locating them from far away was based on color, because they had distinctive colors, and then manipulating them. You saw there is a stereo camera in the back with projected laser, and then estimating the parameters of the cup. We could have done this also with some template matching things, because the objects were known beforehand, but because they are so simple and symmetric, it's actually works just as well with Rensec, or maybe even a bit more robust, because you have inbuilt this information that every rotation around Z is equivalent and so on. Okay, then you're inserting. Then there is one more. Then it found well, it's called battery pack, but it's just a box which you have to find. Here I think we forgot the constraint in that it has to be horizontally on the plane, because it was estimating it a bit off, or maybe it's just Rensec messing up. So it's grasping it a bit not centrally. So you will see this will make some fun. I don't know how to speed it up, unfortunately. Or just let it go. And it was quite heavy, so it was over 1 kilo, I think, and the fingers were not so strong. And it's doing the movement. That's perfect. This was planned, of course, like this. Shot. And of course, we knew that we were running on gravel, so it would then ease into the. No, that was multiple things going lucky. Okay, and this is the difficult part for the. Sorry. Now it has to go back to the base object and put these things in. It's looking for the base object, and you can see how great the data looks from the back camera with the projected laser. You get basically this from that image. So part of it is completely missing because it's the picture ends here, and this is where the image is cut, and you have very narrow sharp angles, and even on the front side you don't see much because it's just a weird type of plastic that even with the projected pattern it was working strangely. But for the Rensec box fitting it was working quite okay. But we needed this occlusion rating to not allow it to go into known free space. And the other thing that we had to do is also the box that you fit it will be always smaller than the regular one, and then we took the real box and moved it around such that it includes the original box but doesn't violate free space constraints, and the edges overlap with the color edges, and so after many checks you get the correct pose, which is important to not also for putting things on top of it, but also to slide in the battery. That's the more critical part, that you have to have the axis and the height relatively correct. So it's doing another estimation just to be sure. And also it has some force feedback, so it has to be really perfectly aligned, but you have to have also some force measurements to push it in. Okay, now you press the switch, and then it was measuring the weight of the cup and then so on. So it was, but this was it, and it was done in half an hour. So it was the vision part was the slowest. So it was like 5x in mileage. So it was processing a lot on. We had I think 8 cores or 16, and most of it was occupied by other stuff. So vision was underfed. So did this quit? Okay, so this is just the LRU with the different modules. The tool it can turn around the fluids, but we didn't use that. And yeah, this is what we just saw in the videos. Hello? Okay, it crashed. So thank you.
Thanks a lot, Sam.
Thanks a lot, Zoltán. Do we have any questions?
Yeah, any questions from the audience?
Which stereo camera were you using for these 2 monocular cameras?
It's inbuilt, yeah. And the stereo algorithm was this semi-global matching, which was developed there at DLR, and it's used actually also in the industry now at Daimler and other companies because it has an FPGA implementation, so that you can get really fast depth.
So you didn't need any camera on the arm?
No, it was, we had to do some hand-eye calibration, and luckily we have an expert for that as well in-house, and that was relatively okay, but yeah, it could have been improved further, but it was just, we had, like, I don't know, half a year or so to work on it, and on the vision part even less, because first it had to be built and everything, so. But it was good enough. The ARM is the only thing which is not by DLR there, and the projector and the components and so on. That was the kilowatt Jacquard, yeah. And we had version number 1 of the second generation. So it was also a bit buggy and so on, but it was enough to do the fine adjustments.
Very good.
Any good more questions?
Which IMU have you used?
That's a good question. I know it's an expensive one. This visual navigation solution is actually commercialized now by a spin-off. It's called Roboception. It's here in Munich. So if you need jobs, probably they are hiring. And they do a cheaper version. I mean, still not very cheap, but cheap enough to be sold to industrial partners. And they do it all on I think Odroid maybe, and cheaper IMU, and everything made into more like mass producible.
Roboception.
Roboception, yeah.